Hello programmers, welcome to the video. So today we will be solving Leetcode daily challenge of October 12, day 12. And today's question is find sum of array product of magical sequences. Okay, let's directly jump. It's hard question I think. Yeah, let it open. So yeah, it's open. There is some internet issue, so it takes some time. Find sum of array product of magical sequence. So let's understand the question first. You are given two integer m and k and an array nums. Okay. The sequence of integer sequence is called magical if sequence has the size m, exactly m size. Okay. Sequence of I should be greater than 0 and less than of nums of length. So nums of length is like 5, so it should be less than equal to 5, less than 5, 0 to 4 range. The binary representation of 2 key power sequence 0, 2 key power sequence 1 till 2 key power sequence m minus 1 has k set bits. Okay, so there is k given to us, and the array product of the sequence defined as product of sequence is nums of sequence 0 into nums of sequence 1 up to nums of sequence m minus 1. Return the sum of array products of all valid magical sequence. So first of all we need to find, like, there is too many sequences. From that we have to filter out some magical sequences, and from that magical sequences, for each sequence we have to do this product and then sum them up. So answer may be very large. It's modulo 10 power 9 plus 7. So what is a set bit refers to a binary representation of a number that has a value of 1. Okay, to understand it better, let's take some example number 1. Okay, its output is too large. I don't think so we can calculate by doing some. Okay, so let's look at example number 2 here. So let me pick the pen and let me explain you through that. Okay, so here, for example number 2, we have given m equal to 2, k equal to 2, nums equal to this array. So nums dot size, what is the nums of size? 5. Nums of size 5. Okay, this is let's call it n. Okay, so we need a sequence. Okay, sequence with basically two elements. We need two elements here, two element sequence, m equal to 2. So we need sequences of two elements. Okay, so a comma b. Okay, a comma b, something like that. We need sequences like that, and also we need k equal to 2 set bit, which will come again later, and a should be like less than 5, greater than equal to 0. B also should be less than 5, greater than equal to 0. Can a equal to b? Yes. Can a should be no, a can be equal b. Okay, so a and b can be equal. Okay, can possible. Okay, now because there is not given in the question that both can't be, like, the sequence of I is unique, there is not given, so we can't assume that, and we are assuming we can add a equal to b as well. Okay, so let's go ahead. We need 2 की power a. Okay, 2 raised to power a plus 2 raised to power b. We have some number num. Okay, this number, if I represent in binary, something like that, 111001110. So how many set bits are there? There should be k equal to 2. Okay, we need two set bits only, not more than that. No, not more than that. Okay, so let's try run on this example. Okay, for this m equal to 2, let me take. Okay, let's go to example. Yeah, here. So for m equal to k equal to, we have nums. Okay, great. So let me clear first. So sequence, what all sequences we can make? Okay, so we can make sequence of a comma b, which is 0 comma 0. Okay, so sequence of I should be less than 5 and greater than equal 0. Okay, so it can be 0 0, yes. It can be 0 1, yes. Then 0 2, yes. 0 3. So you understood, we can calculate for 0 4 and 0 5. So these are the sequences of starting with 0, then we will start with 1, so it's 1 0 1 1 1 2. I hope you understood the request. Okay, so all the sequences will be there. How many sequences will be there? Can we find it? Yes, we can find. How many numbers are there? 0 1 2 3 4. Okay, so basically n numbers are there, and we have m positions. Okay, so for m positions, each position we have n. For each position we have n choices. So it's n raised to power m. That many positions, that many sequences can be generated. N raised to power m sequences can be generated. Okay, 1 comma 2. Let's complete this first. So let me clear this. So here I will write total n raised to power m sequences will be there, and both all 1 comma 3 1 comma 4 1 comma 5. Okay, then I will go with 2 comma 0 2 1 2 2 2 3 2 4 and 2 5 3 1 3 0 3 1 3 2 3 3 3 4 3 5. Okay, and then at last 4 0 4 1 4 2 4 3 4 4 and 4 5. These one sequences. Okay, so I have created in this case n is equal to 5, m is equal to 2, so there will be 25 sequences, which is there. I have calculated all 25 sequences there. Okay, now what? Oh, so let me remove this. Yeah, so now what? Next it is saying us that we need sequence of size m, which we did. Sequence should be 0 to nums, sequence of I should be greater than equal to 0 and less than nums of length, which we did. And the last condition is the binary representation of 2 raised to power sequence 0 to raised to power sequence 1 up to 2 raised to power sequence. Basically sum of all the 2 to the power of sequences should be should have the k set bits. Okay, so let's try run on this example as well. Okay, so let's take 0 0 for example. What will be the answer? 2 raised to power 0 plus 2 raised to power 0, which is like 1 plus 1 is equal to 2. And in what 2 we can write 2 in binary representation, we can write is as 1 0. Okay, how many set bits are there? One set bit only, and we have k equal to 2, so it's not accepted. Because we need 2 set bits, it has only one set bit. Okay, so let's go ahead with example number. Let's go ahead with second sequence 0 and 1. So 2 raised to power 0 plus 2 raised to power 1. 2 raised to power is 1 plus 2 equal to 3. And what we can write 3 in binary representation? 1 1. And how many set bits are there? 2 set bits. So it is accepted. Okay, great. It's accepted. Now let's go ahead. Let's calculate for all of them, something like that. Okay, so I will not write 2 raised to power 0. We will calculate 2 raised to power 0 1 plus 4. It's 5. 5 is 1 0 1. So it has 2 set bits. Then 1 plus 8. 2 raised to power 3 8. 9. 9 has 1 0 0 1. It has 2 set bit. 16. And 2 raised to power 0 is 1. 17. 1 triple 0 1. 1. 2 raised to power 32. 33. 33 is written as 1. 4 zeros and 1, I think. Yes, yeah, so it has 2 set bits. Okay, so it's accepted. Something similarly, if I do 1 0 since 0 1 is accepted, obviously 1 0 is accepted, so we can optimize this further. Like if I am taking 0 1, I don't have to take 1 0. It's the same permutation, like same numbers within different order. Okay, so that we can optimize further and we don't have to go till n raised to power m sequences. This is one observation which we can note here, and we will optimize, like we can leverage this observation after that in the question. Okay, so 2 raised to power 1 plus 2 raised to power 1, 4 has only one set bit 1 0 0. 2 raised to power 1 is 2. and 2 raised to power 2 equal to 4. So 2 plus 4 6, 6 is 110, it's accepted. Similarly 1 comma 3 is accepted. Similarly 1 16 17 18 18 is accepted. 32 and 34 accepted. Okay, 34 now. So one, there is one issue I think. I have like 25 sequences should be there now. 1 2 3 4 5. 1 2 3 4 5. Oh, I got it. So its sequence should be like less than 5 now, so it can't be like fifth wala. So I have to remove this. This is not needed. Up to 4 we can go. We are not having 5. Okay, let me remove this. These sequences are all only there. Okay, so 2 raised to power 0, so 0 2 is accepted, so 2 0 will be accepted. Similarly 1 2 accepted, so 2 1 will be accepted. 2 raised to power 2 is 4, 2 raised to power 4, 4 plus 4 8, 8 has only one set bit, it's not accepted. 2 comma 3 it's accepted, 2 comma 4 accepted. 3 0 because 0 3 accepted, so 3 0 accepted. 1 3 accepted, so 3 1 accepted. 2 3 accepted, so 3 2 accepted. And 3 3, 2 raised to power 3 plus 2 raised to power 3, which is 8 plus 8 16, only one set bit, it's not accepted. This is accepted. And 0 4 1 similar is 4 0, 4 1 similar is 1 4, 2 4, 3 4 and 4 4. 2 raised to power 4 is 16 plus 16 32, 32 only has one set bit. Okay, so we have 4 4 8 4, total 20 sequences. Total 20 sequences we have in our complete scene. Okay, for each sequence we can calculate like nums of 0 multiply by nums of 1. I am taking this one, I am taking this first one, 0 comma 1. For this I will calculate it nums of 0 multiply by nums of 1 plus, then I will do this 0 comma 2. For 0 comma 2 what I will do, I will do nums of 0 multiply by nums of 2. Okay, plus then for 0 3 nums of 0 comma nums of 3, then 0 4. Similarly I will do for all 20 sequences, I will sum them up and I will take mode of them. So mode is here 10 raised to power 9 plus 7, this is mode. Okay, 10 raised to power 9 plus 7 to do modulo, and this is our answer. Okay, so this is a brute force approach. Can we optimize it? Let's check for the first constraints. So here constraints is k and m can be up to 30. So total sequences will be like, how many total sequences will be there? N is maximum 50 and to the power 30. It's huge. We can't do in brute force. So brute force will be giving us TLE. We will surely get TLE if I do brute force, because this many sequence I will generate, and then for each sequence I am checking that how many bits are there, right? So these many sequences, for each sequence I am traversing for summing the 2 to the power 0 plus 2 to the power 1. Okay, and then we are checking that how many set bits are there. So let's say checking set bits take O1 for example. So traversing through this each and every sequence will take m time because it's m size. And then for product also, so let's assume that for product how many sequences are there, these many sequences are there, and for all of the sequences we do summation. So I will traverse them once as well. So this is plus 50 raised to power 30, so it will not add up. So let's remove this, we are not calculating for this, let's calculate for this. And for each number, so let's say we have a 32-bit number, we have to go and calculate how many set bits are there. It should be k, so multiply by 32, which is constant, so let's leave it for now. So we have n raised to power m multiply by m, this is time complexity. And how much space complexity is there? Similarly, o raised to n raised to power m sequences, and for each sequence we have m size. So this is our space complexity. So TC and space complexity of brute force solution I have explained. Let's go and let's try to optimize this, because it will be like giving us T only. Okay, great. Let me remove these drawings first, so only the useful will be there. Yeah, done. So this product part is, I hope so, clear, and we don't have to worry much about this product part, because this is not the one which is like making much difference. We have to optimize for this one. Okay, so let me take the pen. Okay, great. So here, how to optimize this is the question. So remember, we have done one observation, that you have to just pick 0, 1. If I am picking 0, 1, I don't have to pick 1, 0. Okay, I will pick this and I will multiply in reverse order as well, something like that. Okay, so think of it like, because it's repeating 0, 0 can be. Okay, so let's put all these numbers n's in a cluster. Okay, we have a cluster, and in this cluster we have all these numbers like 0, we have 1, we have 2, we have 3, we have 4, and up to 4. Okay, each number is unlimited, each number is available at infinite time, each number is available infinite time. Okay, and we have to pick m elements. M means here 2 elements, so we have to pick 2 elements here. Okay, this is our number of sequences, these many sequences we will get. Okay, we have to pick m elements from the n cluster. So to generalize it, I am like general solution, I will write general solution here. So we have here like 0, 1, 2 up to n minus 1. Let's say up to n minus 1, and we have to pick m sequences from m numbers. From them, each one is available infinitely, so it will not empty them. Okay, I can choose 0 for all the m's. That's quite possible. Okay, great. Now for the example scenarios, let's go here, and I am picking 2 elements. Okay, from these 2 elements, what to check? I have to check how many set bits are there in our binary representation. Okay, so let's say I am taking 2, 2 and 3. Let's say 2 and 3 example. Okay, how to check how many bits are there in their binary representation after summing them up? So 2 ki power 0, we have 1 0. We can write 2 ki power 2 is 4, so I will write it 1 0 0. 2 ki power 3 is 8, so I will write it 1 0 0 0. Okay, now if I sum them up, how many set bits are there? It will be 1 0 1, sorry 1, my bad, it will be 1 1 0 0, which is 2 set bit. Okay, how I get it? If there is the case like 2 raised to power 1 plus 2 raised to power 1, we have to add up its binary representation 1 0 1 0, then it's 0 1 1 0, and then there will be a carry, and this carry will be carried over here, and 1 0 0. This is how we sum the binary numbers. Okay, by using carry. Okay, so we have to account for this carry as well. We have to account for how many numbers till now we have seen, how many set bits are there. So it's 1 set bit till here. Okay, till now how much numbers we have in our array and how much we process. Too many variables here to juggle up with. Interesting. I'm not able to think clearly, like only one observation I made which is helpful. Like I can cut this, and I can visualize this as cluster, and I am picking this m elements from this cluster. Okay, it's n raised to power m numbers to pick this cluster, but this will surely give us TLE. I'm not sure how to optimize that. I am kind of stuck here. Okay, let's look at this topics. What topics are there? Array, obviously array. Maths, okay, some maths are involved. DP, okay, so we have to think in way of DP. Dynamic programming, bit manipulation we are doing. Combinatorics, yes, n raised to power m, this is called combinatorics. Bit masking, okay, these are tags, so we can think in terms of DP. Okay, we can think in terms of DP, what kind of DP we can make here, and how this DP will solve our problem. So wherever DP comes, there comes recursion. So DP is nothing but recursion plus memoization. Okay, memoization. Okay, so if I can figure out the recursion part here. I can store this whatever we encounter in DP and I can use that. Okay, so for this, what to do? We have to think of in a recursive manner. So for recursive manner in a array, we always see that array is smaller first and it grows bigger one step at a time, and we will keep adding in our cluster numbers and we will keep choosing number of elements from them, something like that. Okay, let's look at some hints here. Like, I'm not use dynamic programming. Yeah, I know that. Not much of help. Let DP of ij mask be the state after choosing I number indices. Okay, what is I? I is the number of indices. Okay, so in our example, if I have a array of size n, one minute, yeah, array of size n, and if I have traverse till here, this is where ith index. Okay, I have traverse till here. I don't know about this future upcoming array. I have traverse till here, my search space till here. So at this I indices, after choosing this I indices, I am choosing this, choose I index. Our state will be DP of some I. What is j? I am still not able to understand. What is mask? I am still not able to understand. Okay, so let's go ahead and look at hint number 3. Okay, so hint number 3 is saying the partial sum, as sum is as represented 2 raised to power sequence of 0, 2 raised to power sequence of 1, 2 raised to power sequence of I minus 1, has produced exactly j set bits once you have fully propagated any carries. Okay, so what it is saying to us, that if I have, let me change the color first so it will not confuse us. Okay, so if I have traverse till I minus 1 I have calculated, then I am calculating for DPI, right? Correct. So I have DP of I with me, with some j, with some mask. I don't know the last two elements yet, but for I it is saying that here it is explaining j. So for I minus 1, okay, for I minus 1 we need to calculate DP of ij mask, we need DP of I minus 1, some j and some related to mask. Okay, and here they explain j. What is j? J is set bit. How many set bits we achieved so far? That's the j. Okay, and j should not be crossing our total set bit, which is k. Okay, great. So can we think about it? Still mask is not clear. What is mask? So let's continue with these hints and let's see if we can leverage this. So here the mask represents the window of lower order bits from S that have not been yet fully processed, i.e. bits that might later create new set bits when addition terms are added. Something like carry. If I am carrying something, if I have some digit here, I can add this carry and it will generate as a new bit. So the mask represents the window of lower order bits. It's lower order bit, not higher order. Okay, window of lower order bits from this sum. So we have a sum, partial sum. Okay, and from partial sum we have not yet been processed. Okay, this mask is not processed, so bits that might later create new set bit when additional terms are added. So additional terms which will be added, 2 raised to power sequence of I, which will be added, and this mask will help us to generate set bits. Okay, I understood this concept of mask. Like I understood what's the use case of mask, but exactly what's this mask I still not able to get. Let's continue with hit number 5. Use combinatorics like NCR, NCR and PR, something like that, some factorials kind of thing. So let's leave it for now. Hint number 6 is how many ways are there to permute a sequence of entities where some are repetitive. This is n to power m, which we have already discussed, and we have already visualized it using a cluster, and cluster mein we will use m m numbers from the cluster which can be repeating. Okay, so this looks like a 3D DB problem, IJ mask. Okay, and I'm not able to grab, I think, math part of it. So let's quickly like code this basic one. Like I think brute force we can always code it. It's always better if we are not able to find the optimal solution. We should code this brute force approach. So it will always help us gain some marks in interviews if there is any. And if this kind of question is asked in interview, the interviewer will also assume that it's a hard question. How we approach it's more important. If we are finding the brute force solution, understanding the question and implementing the at least brute force solution will as well like give us some brownie points. It will obviously not sail us through the interviews, but yeah, it's very difficult question. I find like 3DP is very difficult to think of and implement in an interview of 45 minute and 1 hour setup. Okay, so let me code it quickly. So we have nums, so dot size s. Let's generate some sequences. So m size sequences we have to generate, and we will so here I am doing 4 parts. Okay, in brute force, first generate sequences, generate all sequences. Okay, then what I will do, I will check for some of them, sum of 2 raised to power sequence of I of all of them. Okay, then I will check how many set bits are there to find magical sequences. Okay, and then at the last we find product of all magical sequences. Okay, so these are 4 parts of our problem. At least let's tell you through like all these 4 parts one by one. So let's make a private function. Okay, let me name it as, it will not give us anything, generate sequences. This is a function name. It is taking m because we need m size sequences. It will take total n. Okay, because we need 0 to n minus 1 sequences, and it will take vector of int address of sequences, which we will pass and we will add in the sequences. Great. Okay, so for implementing first part, I will make a vector of int sequence here. Okay, and I will say after generating all the sequences, I will have this all of them in SEQ, sequence of array, sequence of vector. Okay, I will have all of them in this. So let's call this generate sequence function, which will generate for us like m comma n comma sequence, what all we need in generating sequence. Okay, how we will generate sequence? First of all, so we will look through all of them. Okay, it's n raised to power m, right? N raised to power m times it will generate some sequences. Okay, so at each location we have two choices, either to include in this sequence, either to exclude. If I am including, then also my sequence size will not reduce, it will keep remaining the same. If I am excluding, like I excluding them, then I will left with the remaining of them. Okay, so I will take a for loop and I equal to 0, I less than to n, I plus plus, something like that. Okay, if I include this generate sequence, so m remain m, n remain m, sequence remain sequence. I need some more information right here. So what included, what's not included, what's the current generated. Okay, yeah, so it should be m size. If it is more than m size, then obviously I will stop. Okay, so I will add vector of int is current, let's say current, what's the current sequence which is running. Okay, and if our current sequence size, current dot size equal m, this will become our base case. We will add in this sequence dot pushback, this current sequence which we are running. Okay, and then we will return from here. Obviously I will pass it as a reference since, okay, so if I am choosing this, what I will do, I will add current dot pushback this I 0, and I will pass this current here. So I have choose this one, and let's remove this after this complete sequence. So dot pop back, something like that. Okay, what's the removal of last element from vector? Oh, let's calculate cpp remove last element from vector. How it's pop back, yeah, the pop back functionality is there. So I will do current dot pop back. Okay, great. So if I am removing this 0, then I will be going to 1, I will push back 1, I am selecting the 1 and I am going ahead. Okay, so here with this for loop I am ensuring that I will generate all the sequences will be marked in this sequence. Okay, great. So for the confirmation that we have generated the successful sequences, let's print each and every sequence for auto sequence as in sequences for item in sequence. I will item with a space, and after that I will return the end line. Yeah, so I can print all the sequences and check that we have generated the sequences in correct order or not. Okay, so let's generate for 5. It is saying there is no functionality dot pop back is not there. Okay, oh, it's semicolon. Generate sequences will be there, it's a void function, and in sequence. Okay, I need to pass fourth argument as well. Fourth argument is current, which I will make here like vector of int current, and I will pass this current sequence here. Let's run it. Yeah, so you can see for m equal to 5, k equal to, sorry, m equal to 5, nums equal to 1 2 3 4 5, so n and m both 5, so we need 5 raised to power 5. So 5 raised to power sequences will be generated. It's 2 hues, so 5 raised to power 5 will be like 3000. So let's look at example number 2. It's 5 raised to power 2, so it's 25. Yeah, we have drawn on this example. So you can see 0 0 0 1 0 2 0 3 all the way up to 4 4 is generated. Okay, all the way up to 4 is generated. Okay, so we are generating the sequences in a correct order. We have checked by printing them, so it's done. Great, the first part is done. Okay, what's the second part? Second part is check for each and every sequence. What we will check? We will check 2 raised to power something, and we will make sure we will have only magical sequences there. Okay, so let's magical sequence. So I will mark all the magical sequences in this new array. Okay, or else you can say that if I found a magical sequence, or okay, for the sake of simplicity, for now let's mark magical sequence in this array. All the magical sequences I will put in this vector. Okay, so how I am going about it? I am going like I do 0 alias. I will do something vector of int sequence in sequences. I will go through all the sequences. I found the first sequence is S, and what to do with this sequence? I have a vector of int. Okay, I will calculate a number, so it can be 2, so I am marking power number. Power here, power is 0 first, and I will add up. So for each element, okay, so it's integer item in sequence S. For each element, what we are doing? We are doing power plus, oh my god, we are doing power plus equal 2 raised to power how much item. Okay, so how to represent 2 raised to power item as 1 less than item. Okay, if it is 1 less than 0, then it is 2 raised to power 1, which is 2 raised to power 0. Okay, something like that, which is obviously 1. And if it is 1, item is 1, then it's 2 raised to power 1, it will be 1 0. If item value is 2, so 2 raised to power 2 is 4, so it will be 1 0 0. Okay, great. So I'm summing all of the power, and at the end let's check how many set bits are there. Okay, if set bit of this power equal k, then I will say it's a magical sequence. So I will add magical sequence dot push back this sequence S. Great. I will find all the magical sequence. Part 2 and part 3 will be like I'm solving together. I just need to make how many set bits are there. So I will make integer function count set bits. Okay, it should be like count set bit. This function is there. I will take a long power here. So I have a long number, and I have a plus only number. Okay, so how to check how many set bits are there? So we will keep dividing it by 2. So while num more 2. Okay, so let's check like this. While number is there, okay, I will do if number more 2 equal 0, sorry, not equal 0, means it's a set bit. Okay, the end bit is set bit. I will add some count, so let's keep count is 0 here, and I will add count plus. Okay, and if it is not, then I will not do count plus, and anyways I am keep dividing number by 2. Great. So to divide the number by 2, I can use num divided by equal to, or I can use like something num greater than 1. So it is also similar. Okay, so I will prefer simplicity here, and at the end I will return this count. These many seed bits are there, and we have magical sequences at the end. Okay, after calculating all the magical sequences, what I need to product it. Okay, I need a product. So first of all I will define a mode. So integer, sorry, long mode value is there, which is 10 raised to power 7. 7 plus 9, right? 10 raised to power 9 plus 7. So 1 2 3 4 4 5 6 7 8 9 and 7. Okay, this is our mode value. And to optimize, I can do this mode operation here as well. So how I will do, I have a magical sequence S. I found it's magical. Okay, so for sequence, what we done, we calculate, we sum the powers, we check if power is k, then we are saying that yes, it's power of k, then we will add in our answer. So we will check int answer equal 0. Okay, I will sum the product. I will add product here, and I will say product plus equal. Okay, I need to loop through this sequence now. This is a magical sequence, correct? So for this magical sequence, I will check int item in this sequence as. Again, I will do this for loop. Okay, can I do this here and this add, just add in the power? Okay, it will like, okay, it will not reduce our time complexity much, yeah, but it will reduce one for loop here. Then I will add something like int temp product equal 0, and I will add product plus equal temp product. I will explain what I am doing here. Okay, so I am adding temp product here, and I will only if count set bits is k. If it is not k, I will not add, but in any case I will add. I will calculate temporary product here with these items. Okay, so how I will calculate temporary product, it will be like, we have item. Okay, we have item of sequence, so it's nums of multiply equal now. So I will keep it 1. Okay, temporary product is 1. I will multiply nums of item. Okay, this is how I'm calculating temporary product. And after calculating all the temporary products, okay, here also I need to make sure that I am keep doing the mode operation here, otherwise it will be like more than 10 raised to power 9. Yeah, mode operation. So it will product. Great, I will add in 10 product, so I will also make sure here before adding in the 10 product that we are doing mode operation here as well. Mode. Okay, okay, great. Now we have all the product with us, we can return this product at the end. Okay, find product is, this part is also done. We have done all these parts, 2 3 4, all the parts are done in short code, and I will return product here. Okay, so let's try to run this, and let's see if these test cases are passed or not. At least these test cases should be passed. There is a issue. So item. Okay, so it's, I will make it long. It will help us. Yeah, all the 3 test cases are passed. Let's submit it and see if we are getting TLE. If it is, obviously we will get TLE, but how many test cases are passed? Let's see. Yeah, I am getting TLE for m equal to 9, k equal to 5, 1 2 3 4 5, 5 raised to power 9. We are not able to calculate because 5 raised to power 9 is 19,53,000 some sequences. These many sequences are generated, and for each sequences we are multiplying this with m. So it's n to the power m and multiply by n. It will exceed our TLE. Okay, so it's 10, more than 10 raised to power 7, and for each 10 raised to power 7 also we are calculating for each k bit. So I think it's exceeded. How many test cases passed? 252 out of 528 test cases passed. Basically our solution is correct, like approach is correct, but it's brute force. We need to optimize it further just to submit this problem. Okay, and I'm not able to come up with some more optimizations here. I did something here, I can like optimize little bit of here, but it will not make much sense. basically all of the optimization we have to do by dynamic programming, which they have told that we don't have to generate the sequences, we have to keep a cluster, and from the cluster we choose m elements. Okay, we don't have to generate all these things. Okay, so this magical sequence we are not using this, so we can remove this as well. Let's directly jump into the editorial and let's see if we can sail through this, and let's get some intuition using dynamic programming. Okay, so let me clear these drawings first. Yeah, all of them is cleared. Is anything useful here? No. So let's clear. Okay, so it is saying let the length of nums n according to 0 to n minus 1. We have seen, suppose that rt elements with values t, then we have 0 to n minus 1. Okay, r of t equal to m, and number of arrangement of these sequences is m factorial. Okay, some combinatorics is getting used here. My bad, let me just zoom it here. Okay, so it is saying that t equal to 0 to n minus 1, we will use sum of t, we will not use all of them. If I am using all of them, we can use all of them as well if m is greater than n. So it is m factorial divided by r factorial, and r factorial of all the r factorials. So it's like, if you see, it's like if t is equal to 0, then mc r0 plus mp. Okay, because all the permutations we also find mp r1 plus mp r2 plus mp r3, something like that. Okay, so what is r0 here? Let's suppose there is rt elements, like r0 elements, which value to t, which value is equal to t. Okay, similar, something like we have a cluster, we have a 0, we have a 1, we have 2, we have 3, we have 4, we have 5, and we have to choose 3 elements from them. So what's the combination we can choose? We can choose how many zeros we have choose. We can choose m is like 3 here, so we have to 3. So out of 3 we can choose like 1 0, plus we can choose how many ones, we can choose 1 1, plus let's choose no 2s, let's choose no 3, let's choose only 1 4, and let's choose no 5. Okay, so these many are ways through which we can choose. This is in this which I have choose 1 2 and no 3 no 4 and 5. I choose 2 0 to 5 only, one amount of 0, one amount of 1, and one amount of 4. Okay, all other elements we haven't picked, so it's 0. Okay, so this is the combinatorics, how many ways we can choose. Then we can sum this with all of, okay, we have to product all of these with sum of the product of the corresponding sequences. These are number of ways, multiply by, for each way we have to do this summation of nums of t raised to power rt. Okay, so if nums of 0, nums of 1, nums of 4 we have to do. For other things we don't have to do here, because its power 0 is 1 only. Okay, then it will come out to be m factorial, and formula comes out to be 0 to n minus 1 rt nums of t rt. For a set of number x, we define mask x as 2 raised to power x. I think it's becoming more complex for me now. I'm not able to like grasp it properly. This is 3ddp IJP, p denotes here mask. So I hope you go through this problem, understood the code. If you are also able to understand, let's discuss in the comment section here. Comment out on this video if you found any intuition, and we can like solve in a better way. It's calculating a quick multiplier function, which is like multiplying something, moding. This is number of size, mode, they have defined a factorial, they have calculated factorial for all, then I factorial, then they have calculated quick multiply I more factorial, then they have nums of power. It's a complex, like complex solution. You can see this complex solution. If I am using for loop, like four for loops inside one each other, then it's obviously too much complex, and five for loops. So yeah, so I'm not going ahead with this. I'm just copy pasting this code. Let me copy paste the solution. Let's submit it for the sake of completion of this 2 days challenge, but I'm not going ahead with implementing it. Okay, so let's look at some solution. If I found something, okay, it is also explaining by using maths and tuition. Some brute force approach we have already implemented. DP state, yeah. So they are explaining DP state as position carry used once. Okay, use 0 to position -1. Carry is the number of bits carry over. So in bit summation we do some carry. Used is the total picks, how many total ones we have picked till now. We have to pick only till k, and have, okay, till m we can pick. Okay, have one set bit, so how many set bits are there, we can have up to k. So this is 4D DP kind of problem. Okay, this is 4D DP kind of problem, and you understand this problem, and if you are able to understand, let me explain as well. So for now I am closing this video. Let's meet tomorrow. I hope tomorrow's question will be like easier than this. Happy coding till then. Happy programming. Bye.